So this chapter is about force vectors, and this chapter is divided into 6 sections. In section 1, we're gonna study scalars and vectors, because many physical quantities in engineering are measured by either scalars or vectors. The next section would be about vector operations, in which we'll study multiplication and division of a vector by a scalar, and vector addition and vector subtraction. Next section would be about vector addition of forces. And in the next section, we will study addition of coplanar forces, where we will study scalar and Cartesian vector notation. The next section would be about Cartesian vectors, and the last section would be on dot products. Now, what is a scalar or a vector? Any physical quantity in engineering are either measured by scalars or a vector. So let's go ahead and define what is a scalar and what is a vector. A scalar is any negative or positive physical quantity that can be completely specified by its magnitude alone. And the example can include length, mass, time. A vector, however, is a physical quantity that requires both the magnitude and a direction as well for its complete description. Examples of vectors can include force, position, and moment. A vector, we have graphically shown here a vector by an arrow, and the length of that arrow would represent a magnitude of the vector, and the angle between any axis, let's just say this is an axis x, some reference point, and the angle theta would represent a sense of direction, and this head or a tip of an arrow indicates that this is the direction of that vector. Okay, so now we will discuss 3 types of vector operations here. One, if a vector is multiplied by a scalar, then how we can multiply a scalar by a vector, and then the next 2 sections would include vector addition and vector subtraction. Now, a scalar can be anything, like for example 0, 1, 2, 3, and so on, and similarly -1, -2. This is an example of a scalar. Now, a vector, as we have discussed before, is represented by an arrow, where this part is called tail of a vector and this part is called head of a vector. So now if we want to multiply this vector by some scalar quantity, then that scalar quantity will change the magnitude or a directional sense of that vector. So let's just say we want to multiply this vector by this scalar 2. So what will happen is that this vector magnitude will get multiplied by 2. So for example, originally it was this much of magnitude. So now by multiplying by 2, you're gonna double the length of that vector. So basically its magnitude will become double, but its direction will remain the same. Now similarly, if we want to multiply this vector by a scalar quantity -1, if we want to multiply this vector by -1, so its magnitude will not change, but direction will be changed. It will reverse in the direction. So if we multiply this vector by a scalar quantity -1, then its magnitude will remain the same, that is this length, but its direction will become opposite. So that's how you multiply a scalar with a vector. Now, how to do a vector addition? Now in vector addition, we have 2 vectors or 3 vectors or multiple vectors, and we want to add those vectors. Adding a scalar quantity is pretty simple, right? We have 2 and then we have another quantity 2. Now if we want to add these 2, 2 plus 2 would be 4. That is an example of scalar addition. Now if we have 2 vectors, now how to add 2 vectors? Now we can add 2 vectors by 2 laws. One is called Parallelogram Law of Addition and another is called Triangle Law of Addition. Now for example, we have this vector A and we have another vector B, and we want to add these 2 vectors. Now parallelogram law says that we have to first, for example, let's just say this is a vector A. Now in order to add a vector B with A, we have to put the tail of vector B towards the head of vector A. So I will just move this vector B and put it on the head of vector A. It would be something like this. So this is a vector B. Now we have to draw parallel lines. For example, this is a vector B. I have to draw another parallel vector, but on the tail of vector A. So this is exactly vector B, but I have drawn it on the tail of vector A. Similarly, I will put this vector A parallel in this way. So now this line is called diagonal of A and B, and this diagonal actually represents the resultant. So if we want to figure out what is the resultant of two vectors, so we have to draw a parallelogram like I've drawn here, and then this diagonal would represent this resultant of that vector. So that's how we find the resultant of two vectors, by using parallelogram law of addition. Now there's another law which we were gonna use in the rest of the lecture series, is called triangular law. And triangular law is pretty simple. You have a vector A, and all you have to do is similarly put the tail of vector B onto the head of vector A, like this. You had vector A and you put this vector such that the tail of the vector B would be on the head of the vector A, like this. Now all you have to do is to join this tail of vector A with the head of vector B, and this new vector would be a resultant vector of A and B. You can also do similarly. Instead of putting the tail of vector B onto the head of vector A, you can also put the tail of vector A onto the head of vector B, like shown in this example, and the resultant would be the same. Now the third subject in this section is vector subtraction. Now vector subtraction is nothing but a vector addition, but all you have to do is to reverse the direction of one of the vector. For example, you have vector A and you want to subtract vector B. So all you have to do is that you have to multiply a scalar minus 1 with the vector B, like we did in the multiplication by a scalar. So you have vector A, you have vector B. Now you have to subtract vector B with the vector to the vector A. So what will you do? You will reverse the direction of the vector B, and you will add similar what we did in vector addition. So the new vector, this was vector A, and when you reverse the direction of vector B, then this was the new vector, which I will say vector B, negative B. So you will use similar rule. You had vector A, you put tail of vector B onto the head of vector A, and this is the resultant. So you had vector A, you put the tail of vector B onto the head of vector A, and this is the resultant, and that's how you subtract two vectors. Now the next section is on vector addition of forces. In this vector addition of forces, we have three sections: finding resultant, finding components, and addition of forces. Now we know that this subject is about effect of forces on bodies. So experimental evidence have shown that a force is a vector quantity, since it has a specified magnitude and direction. So the forces will also add accordingly using parallelogram or a triangular law. So if we have to find the sum of two forces, like for example you have force 1, you have force 2, and if you want to find the resultant, so you will use same principles which we have studied in vector addition, and you can find the resultant of these two forces as well. So for example, let me try to use a triangular law to find the resultant of these two forces. So this is a force 1, this one, and what I will do is that I will put the tail of force 2 onto the head of force 1. So it would be something like this. So what is the resultant? The resultant is from tail of F1 to head of, so this is the resultant force, as you can see from here. Now previously what we have done is that we had two forces, and if we want to find the resultant force, so we apply a triangular law and we try to get the resultant force. Now sometimes we also have to find the components of these forces. For example, you have a force, this one, and you want to find the component of the force. Before we were adding the forces, now we have a resultant force and we want to figure out how many components, or if we want to divide it into different components, so how can we do that? So in order to resolve these into the components, we have to define in which direction we need to find the components. So for example, I want to find the component of this force in this axis and in this axis. So for example, in this case, we have a force which is represented in a blue line. These are the two axes where we want to figure out the components of the force. So all you have to do is that from the tail, you have to draw a straight line, and these can be represented as a component of a force. Now later we're gonna quantify these forces. So for now, we just have to understand how graphically we can represent the component of the forces and forces, resultant forces itself. So for example, we have two components, Fu, Fv, and we have to figure out what is the resultant. So similar, right? We can use the triangular law and we can find the resultant of these forces. Now, if we have multiple forces, we have F1, we have F2, and we have F3, and if we want to figure out the resultant of all these forces, then what we will do? For example, in this case, we have a force F1, we have a force F2, and we have a force F3. Now all we have to do is to add these forces. Now we can do it stepwise using the same triangular rule. This F2, I will put the tail of F2 onto the head of F1, and this force would be called F1 plus F2. So now what we have, if I'm just gonna simplify this, now what we have F3 and we have F1 plus F2, because I've added F1 and F2, so I can just remove these F1 and F2, and all we have is this. Now if I want to add this force with this, all I have to do is put the tail of this vector onto the head of this vector. So it would be something like this is F3 and this is F1 plus F2. So this is the resultant, which we can say is F1 plus F2 plus F3. So even if you have 3 forces, 4 forces, 5 forces, you can add by using triangular law, by simply adding one force with the other and then one force with the other, and you can follow these steps. Now we can do one example. So for example, you have these two forces, F1 and F2, and let's just say we want to find resultant force. Now in this example, we have to remember this is a law of cosine, but later we're gonna figure out a way where we don't have to remember all these formulas. But for the sake of this example, we will use law of cosine, which you can get from any course from trigonometry. So what this law says, let's just try to figure out this law and then we'll find the resultant of F1, F2. So if you have a gamma here, so you can calculate the C, which is length of a triangular triangle opposite to that gamma. If you know gamma, if you know alpha A and you know B, you can figure out the length. Now, this, I will just draw a free body diagram here. So this is our force F1, which is 100 Newton. This is our force F2, which is 150 Newton. Now first, what we will do, we will add these two forces to find the resultant of the force. Now how to add these forces? This is F1. We will put the tail of F2 onto the head of F1. Then you will get something like this. So this is F1, this is F2. What is the resultant? This is the resultant force Fr, which we have to find. Now we're going to try to find what is the resultant of this force. Now, if we know this angle, let me say this is gamma. If we know this gamma, and if we know F1 and F2, then opposite of gamma is C, which is represented by Fr. So we can find this Fr. So we know F1, which is 100 Newton. We also know F2, which is, how much it is? It is 150 Newton. So all we have to do is to know what is gamma. So how to know gamma? Let's see what we have. We are given with, if I draw a straight axis, so we are given this, which is 15 degree. And if I draw straight axis this, we are given this thing, which is, I guess, 10 degree. So how to find this? We know that this is 90 degree, this is 90 degree. So 90 degree minus 10 minus 15. So in this way, you're gonna get 80 and 70, you're gonna get 65 degree. So this is 65 degree. Now we know if this is 65 degree, this is also 65 degrees, because we use parallelogram law before, and or a triangle law. So in parallelogram, this angle is equal to this angle and this angle is equal to this angle. So anyways, this is 65, this is 65, and we know that the total angle of a triangle is 180 degree. So 180 degree, you have minus 65 this, minus 65 this, you will get this gamma angle. So you have to minus 65 degree 2 times, and that's gonna come up with 612, 130, 130 minus something, I guess 115 degree or something like that. So all you have to do is input the values. Now let's use this formula. C is Fr, and A square is, what is A? A is 100 square plus B is 150 square minus 2 into 100 into 150 into cos of 115 degree. And if you try to solve this, you will get the resultant force. Okay, so let's go to next section, which is on addition of coplanar forces. Now, when a force is resolved into two components, like we have also resolved one force into two components, but if these components are rectangular, then that system is called rectangular component system. And this is very important, because when something is rectangular, then it becomes much easier to solve. So then we don't have to remember all these formulas. So in the notation system, there are two types of notation system. One is a scalar notation system, and another is a Cartesian vector notation system. So we're gonna go through both of them in a simple way. So for example, this is an example of a scalar notation system, and this is an example of vector notation system. Now remember, from now on, we will resolve the force vectors into rectangular components. So for example, first let's just draw an axis. Let's just say this is a rectangular component system because one axis is horizontal, another is vertical, and the angle between them is 90 degree. So this is a rectangular component system. Okay, so once we have this system, this is x-axis, this is y-axis. So if there is any force, we can resolve these force into two components like we have resolved before, but before the angle was not 90 degree and now the angle is 90 degree. So one of the force would be this and one of the force component would be this. Let's just call this component of the force f of x, let's just call this component of the force f of y, and the angle between them would be theta, just represented in this component. So how to find the values of f of x, f of y, or f of z? So we know from trigonometry that sine theta is equal to perpendicular over hypotenuse. Cos theta is base over hypotenuse. So if we want to figure out f of x, we know theta, we know perpendicular, and we know hypotenuse. This is hypotenuse. The opposite to 90 degree would be hypotenuse. So if we use this, we can then find f of x is equal to f cos theta. Similarly, if we use sine formula, we'll get y component. And if we add, so what is the resultant? Resultant of f is f of x plus f of y, which is represented here. So this is the resultant force F, and we can also calculate the f of x and f of y components. So we don't need to remember any law of sine, law of cosine type of formulas. Similarly, if we change the notation to a, b, and c, then we can calculate the f of x or f of y by using these formulas. And these formulas come again from this trigonometric rules. Now, this is a scalar notation system. In vector notation system, all we have to do is that, the force is f of x plus f of y. Now, if we put I on the x-axis and j on the y-axis, then we can represent this as a vector notation. So in vectors, the x-axis and y-axis are replaced by this notation I and j, and we're gonna understand about these notations in much detail later. But now I just have to show you that we can also represent the forces in terms of vector notations like this. Okay, so we can do one more examples to figure out. Now in this example, we have to determine the magnitudes of projection of f. Basically, it's represented here. This is a projection on this axis, and this is the projection on this axis. Now, in order to use this formula, f of x is equal to f cos theta, or f of y is equal to f sine theta, we need to have a 90 degree between these two components. Now, in order to find this, let's just say this is a component, this is a force F, which is equal to 100 Newton, and we have a horizontal component, it's written as U here, and this is a F of X or F of U, and this force is F of Y. Now we need to find this, and we also know the formula for f of x is equal to f cos theta. So all we need to know is this theta. If we know this theta, which is 45 degree, we can calculate f of x. So f of x would be equal to 100, which is the force, and cos of 45 degree. So if we solve this, we can get this f of x component. Now in order to find this component, what we can do is, we know this force F, and all we have to do is to find this component, which is f of v. Now, again, in order to find this component, we need to have 90 degree, but luckily we have this angle which is 90 degree. So if we know this theta, which we already know, which is 15 degree, so we can calculate f of v by using the same formula. So these two formulas are written here. We have f of u equal to 70. If we put the values, we'll get 70.7 Newton. And for this projection, we'll get 96.6 Newton. So that's how we can use these notations, and that's how we can use these formulas to get the resultants or components of a force. Now, the next section is regarding to Cartesian vectors. So for example, if we have problems that are in 3 dimensions, so that can be greatly simplified if the vectors are first represented as a Cartesian vector form. So what do I mean by this? For example, first we have to figure out a coordinate system. So one of the coordinate system is called a right-hand coordinate system. So this is a rectangular coordinate system in 3 dimensions, x, y, z, but this 3-dimensional coordinate system would be called a right-hand coordinate system if it follows this right-hand rule. A rectangular coordinate system is said to be right-handed if the thumb of a right hand points to the direction of positive z-axis. So here you can see this is x-axis, this is y-axis, and this is z-axis. So if a thumb is pointing, for example, this is that z-axis. If a thumb is pointing towards the z-axis, if you curl the fingers from x-axis to y-axis, then this type of coordinate system is called right-hand coordinate system. So you don't need to worry about this for now, but it's a type of a system where you have x-axis and you have y-axis, and your z-axis points to the thumb of right hand pointing upward. So this is how you define a right hand coordinate system, which is important because then it would be easier for you to understand the directions of different vectors. So let us take an example of this vector A, and these are the axis. This is x-axis, this is y-axis, this is z-axis, and you have to resolve these components into x, y, and z. So similar like we were doing before, we can also do in this case. So this resultant force A, and we can calculate by adding the components, individual components in different directions. And if you want to replace this by a Cartesian vector, so all we do is that we'll add I, j, or k. Instead of adding sine theta or cos theta, we can just add this I. And in order to find magnitude, we can use this formula to calculate the magnitude of this vector. Now, this is the last section, which is regarding dot product. Occasionally in statistics, we need to find the angle between these two vectors. Now we can find the angle between these two vectors by using trigonometry, since geometry is easy to visualize. So we have done this before as well. We have one force, we have two force, and we want to figure out the angle theta between them. So we can figure out by using trigonometry. But in 3 dimensions, however, this is often difficult, and consequently vector methods are needed. So the dot product is a particular method for multiplying 2 vectors, and we can find an angle between these 2 lines as well. So let us define what is a dot product. A dot product, or a scalar product, it can also be called a scalar product, is a measure of how closely 2 vectors align in terms of direction they point. So basically what they are saying is that a dot product will give you a sense of measure between these 2 vectors. And mathematically we can define this dot product as a product of their magnitudes and cosine of angle between them. So a dot product is a product of magnitude of two vectors and cos of theta between them. So by using these, we can also calculate the theta, or we can also calculate different magnitudes. So now there are three laws which we need to follow for dot product. One is commutative law, another one is associative law, and another one is distributive law. So the commutative law states that if you have a dot product of two vector a dot b, that would be equal to b dot a. And associative law states that if there is a scalar and you multiply that scalar with a dot product of a dot b, then it does not matter if you multiply that scalar with a and then make a dot product, or you multiply that vector with b and that then make a dot product with a. So the distributive law states that you have two vectors b and d which you're going to add, and then you're going to take a dot product with a. So you can also write this, for example, you can also take a dot product of a with b, and you can also take a dot product of a with d, and then you can just add them up. So the result would be the same. This is the end of this chapter, so see you in the next chapter.